This is section 6.4, part 1, simplifying square roots. So this is different than 6.3 where we just estimated square roots, but you might notice that for the warm-up we are going to estimate the value of the square root of 39. So this is just a review of 6.3. So it does say to the nearest integer. Remember, integers are whole numbers including negatives, so you could have -2, -1, 0, 1, 2, 3, 4, 5, 6, etc. There you go. So the square root of 39, what two perfect squares does 39 fit between? So if I'm thinking of perfect squares, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, 6 times 6 is 36, 7 times 7 is 49, and there we go. 39 is right between 36 and 49. Now, is 39 closer to 36 or is 39 closer to 49? 39 is only 3 units away from 36, but 10 units away from 49. So 39 is much closer to 36 than 49. Therefore, the square root of 39 is approximately equal to the square root of 36, which equals 6, because 6 times 6 is 36. So the square root of 36 is 6. All right, there we go. That is the estimation of the square root of 39 to the nearest integer. But again, today we are going to be looking at simplifying square roots, which is different than estimating. So today we're going to use two properties. Here's the first one, the product property of square roots. And actually, now that I said that, let me just verify. No, I'm sorry, we're only using one property today. That's why I split this into two parts. So the one property we are using today is the product property. Product implies the result when you multiply. So here we're multiplying underneath a radical, underneath the square root symbol. What this property says is that if we are multiplying beneath the square root symbol, you can split those up into their own square root symbols. Now you could also go the other way and combine them back together. Since it's an equal sign, it works both ways. So here's what I mean with using that. This says simplify the expression. Now, of course, you could just do 4 times 9, get 36, and take the square root and get 6. I'm trying to build your skill with this problem because down the road you're going to see much more complex problems where that will not work. So if we use the product property of square roots, where if I have a product beneath the square root and I break it up into its own square roots, I could say that this is really the square root of 4 times the square root of 9. Well, what is the square root of 4? That's easy to evaluate. That's 2, because 2 times 2 is the square root, because 2 times 2 is 4. What's the square root of 9? It's 3, because 3 times 3 is 9. What's 2 times 3? Well, it is 6. So we got there a different way, but it is still valid. I'm showing you that that is another way you could evaluate this problem. Take the square root of each value separately and then multiply them together to get your result. Example number 2, this one is a little bit different. This says right in the problem here, using prime factorization, we're going to simplify this expression. So what does prime factorization mean? Well, in other words, we are going to use a factor tree. If you still don't know what I mean, that's okay. Factor tree. Don't mind me. Just drawing a tree. Maybe I should make that green. Summer's coming, right? There we go. All right, a factor tree. So what we're going to do to build a factor tree, I'm going to take the number 20, and I'm going to try to break it up. What times what gives me a 20? So 4 times 5 is 20. Now, I'm going to stop right there. When I build these factor trees, I'm going to stop when I either get a perfect square, like 4, or a prime number like 5. So what's a prime number? A prime number is a number that is not divisible by any other number except for 1 and itself. So if you try to take 5 and divide by 2, you're going to get a fraction. You're not going to get a whole number. So in order to be divisible by a number, you'd have to divide it by the number and get out a whole number. A perfect square is a number where if you take its square root, you get a whole number. So the square root of 4 is 2, so it's a perfect square. All right, so why did I want to do that? Well, if I rewrite 20 using these numbers, 4, that perfect square, and 5, that prime, if I rewrite 20 as 4 times 5, now I can apply that product property of square roots from this slide right here. If I apply the product property of square roots and I separate these into their own square roots, I can take the square root of that perfect square. It's the square root of 4 is 2. So I was able to break something out of the square root, and that's what it means to simplify these square roots, is break out as many numbers as you can from that radical, from that square root symbol. So I was able to break out a 2 because I could take the square root of 4. That 5, unfortunately, is stuck beneath the radical beneath the square root symbol because it is not a perfect square, but that is the simplified version of the square root of 20. So it's not a rounded answer, it's an exact answer. You didn't just plug it in your calculator, so you don't want to do that. If it says simplify, you don't want to just plug it in your calculator. You want to break that value down using prime factorization. It's a fancy way of saying a factor tree. And then take the square root of all those perfect squares that you can. All right, let's try another one. Simplify using prime factorization. It's the same thing as the last one, except now we're using 50. So what times what gives you a 50? Well, some of you might think 10 times 5, and that would be fine. On this one, I'm actually going to show you two ways. So let's say right away you think, hey, 25 times 2. That's what comes to mind. Well, hey, 25 is a perfect square, and 2 is a prime number. So again, we stop these branches of our tree whenever we see a perfect square, or a prime number. So I can rewrite the square root of 50 as a square root of 25 times 2. Use that product property where I separate them into their own square roots. And then take the square root of 25, which is 5. And 2 is just a prime number. It's not a perfect square, so it's stuck inside that square root. So 5 root 2 is the simplified version of the square root of 50. Now I told you I was going to show you two ways. So let's say you look at the square root of 50. Let's say you see this problem here and you go, okay, I can build a factor tree for that. 50 is, let's say you don't see 25 times 2. Let's say you see 5 times 10. Well, 5 is prime, so I can circle that one. This is a prime number. 10 is not a prime nor a perfect square, so I can break this down even farther. 10 is 2 times 5. Those are prime numbers. So now we've got primes all over here. So 50 is 5 times 5 times 2. 5 times 5 times 2. Well, how does that help me move on with this problem? Well, in this case, what I can do is rewrite 5 times 5 as 5 squared. I still have times 2. And now I'll use that product property where I can split these up into their own square roots. The square root of 5 squared times the square root of 2. The reason this helps is because a square root and square are inverse operations. They cancel each other out. If you ever have a square root of a square or a square of a square root, they just cancel each other out. Scribble them out. They're gone. All that's left is the 5 and this root 2. 5 root 2. And sure enough, that's the same answer as what we got over here. So if you see those perfect squares, it will make your life a little bit easier here. You can just take the square root and get that value. If you don't, you have to break down numbers a little bit farther and then write them as the value squared and then cancel out the square root. But you can still get there if you don't see those perfect squares right away. So I just want to show you two different ways. So this is ultimately way number 1, and way number 2. Two different ways of getting the same answer. All right, moving on, just to show you what else we have to go. Nothing after this one, so hang in there. All right, so simplify this expression using prime factorization. Same directions, just slightly different problem because now we've got a constant out in front of the square root, but it's really not a big deal. We're just going to carry this 10 down throughout our problem. So we'll have 10 times something. So just ignore the 10 for a little while, focus on the square root of 250. So again, it says prime factorization, so we're going to build the factor tree for 250. Yes, it's a big number, but that's okay. It's 250. Think money. What goes into 250? Maybe you're thinking 25. That's a perfect square. That'd be a good option. Maybe you didn't see that and you're thinking 10 because it ends in a 0, or maybe 5 because it ends in a 0. So there are a lot of different options. You can even think of 2 because it's an even number. There are a lot of different options when you build these factor trees, but ultimately you're going to end up with one of these two ways as you're breaking these down. One way where you see all the perfect squares and one way where you don't, and then you just have to take a different path, and that's okay. So maybe I should do this one in the two ways as well. So let's do one way where I see all those perfect squares. I'm going to use the same colors that I used in the last one to really make my point here. So I was using black on the left here. All right, so let's say I see, hey, 250, there's a 25 that goes into that. If I'm thinking money, every 100 has 4 25s, so I've got 4, 8, 10 25s, 25 times 10. Okay, so that's a perfect square, so I'm going to circle that. Now 10 is not a perfect square nor a prime, so I need to break down 10 into 2 times 5. Those are both prime numbers, so now I can circle those. So I have 10 from my original constant out here, times the square root of 250 is the square root of 25, times 2 times 5. Those are just from my circled numbers here. I can break these up using that product property of square roots. And then I try to take the square root of as many of these square roots as I can. So the square root of 25 is 5. So I have 10 times 5. The square root of 2, that's not going to happen. 2 is a prime number. Square root of 5, that's not going to happen. 5 is a prime number. So all I can do here is leave them alone. And ultimately, I'm just going to multiply 2 times 5 back together to get me the square root of 10. My last step, now that I've carried this 10 throughout my problem, is just multiply the two constants out in front together and get 10 times 5, or 50 root 10. And that's the answer. So that's if you saw that perfect square right away. So again, let's say this is way number 1. Well, let's say you don't see that perfect square right away. How would you approach it then? So if I have the same problem, square root of 250, 10 root 250, I should say. How do you approach that problem if you don't see that perfect square right away? So if you say, okay, I've got 250, it's an even, so 2 must go into it, 2 times 125, and then, oh, I don't see that 25 goes in there, 2 is prime, I should circle that. Let's say it ends in a 5, so I know 5 goes into it, 5 times, oh, no, because I'm going to get that 25 back again. Well, that's fine. So let's say you don't see that 25 is a perfect square, so you keep breaking it down, and you get 5 times 5. All right, so let's say you break it all the way down into prime numbers. So you could always do it this way if you really wanted to. I mean, it just makes your life a little bit easier if you find those perfect squares. But let's just say you have trouble thinking of perfect squares. You could break it all the way down to prime numbers every time. You could always do this way number 2, and that's fine. It's just going to take a little bit longer, but that's okay. All right, so if we do it this way, I have 10 out in front here times the square root. 250 is 2 times 5 times 5 times 5. Well, just like on this last example, I was trying to make a number squared because the square root and square canceled each other out. I'm going to do the same thing here. What squared is hiding in these 4 numbers? Well, I have a 5 squared. I have at least 2 5s in there, so I can have a 5 squared. 5 squared times 2 times 5. My 10, again, gets carried down throughout my problem. I can use the product property of square roots to say the square root of 5 squared times the square root of 2 times the square root of 5. So each one of these gets its own square root instead of all being underneath one square root. Well, again, right here, the square root and square will cancel out just like that last example. So I end up with 10 times square root and square are gone. I just have the 5 left over times the square root of 2 times 5, or the square root of 10. Well, 10 times 5 is 50, root 10, and I got the same answer either way. So it doesn't matter how you get there. Either way will work, whether you see those perfect squares or not. So that brings us to the assignment. It is a worksheet simplifying square roots, and as promised, I will go through the odd problems with you. On this one, it is double-sided here, 24 total problems. I'm going to do 12 of them with you. You have to do the other 12, but also copy down the work as I do it on here. So here we go. All right, so square root of 96. 96, if I try to break that down using my factor tree, it's even, so I know 2 goes into it. So I'm just going to pull out a calculator here and do 96 divided by 2 and get 48. So I'm going to just say 2 times 48 is 96. Well, 2 is prime, so I can circle it. If I break down 48, it ends in an 8, that's even, so 2 times 24. Circle the 2 because it's prime. 24 is 2 times 12, 2 is prime. 12 is 2 times 6, 2 is prime, and 6 is 2 times 3. Those are both primes. So on this one, I didn't think of any of those perfect squares that could have gone into 96. I mean, sure, I could have thought of a 4 or even a 16, but I didn't think of those when I was doing this. I just got all my prime numbers, and that's fine. So the square root of 96 is the square root of, I'm going to try and pair all of these up into squares. I have a 2 squared there and a 2 squared there, and then just a 2 times 3 left over. 2 squared times 2 squared times 2 times 3. If I break each one of these up into their own square roots, I'm going to start skipping the step coming up, but I'll break each one into their own square roots. The square root and square cancel out here, so this turns into a 2. Square root and square cancel out there, so that's another 2. And then the square root of 2, there's nothing to cancel out here because it's not squared. Same thing, the 3 is not squared, so combine them back together. 2 times 3 is 6. And your last step is multiply the 2's together, get a 4 root 6. Number 3, we have a 98 instead of a 96. So it's close, but not quite the same. So 98, what does that break down into? So on this one, if I take out my calculator and I take 98 and I just start looking for some large numbers that go into it. I know 2 goes into it. 2, oh, there you go, 49 and 2. The reason I like that is because 49 is a perfect square. That's 7 times 7, and 2 is a prime. So on this one, it's the square root of 49 times 2. The square root of 49 times the square root of 2, which is 7 root 2. There's the answer to that one. Now, I'm going to provide you with the answer key on this one as well, so you can check your answer. Like, let's say I just finished this problem, and here I got to 7 root 2. I'm correct there. But when I go and grade this, if all you put is these answers, I will give you no credit. So you have to show your work on these. The only exception is a problem like, let's see if I can find one on here, like on number 17. The square root of 36 is a perfect square. 36 is a perfect square. So the square root of 36 is just 6. So you could really just put 2 times 6, which is 12. So that one requires very little work. Number 6 requires no work because the square root of 144 is just 12. So that's the exception. On all of the other ones, though, you should be showing me some work. I don't believe there's any other perfect squares that you have on here. Yeah, so on all of these, you're going to notice that they all have 20. You could at least show me the square root of 1,764. Just plug that in your calculator and then multiply by 12. So at least give me the value of this square root and then write that 12 times whatever that number is, and then you can write 504. So at least give me that much, but all the other ones have a square root component with them. So please try to show me some work just like I'm doing here. All right, number 5, 72 breaks down into 36 times 2. That's a perfect square and that's a prime. So square root of 36 times 2. Square root of 36 is 6. And I have the square root of 2 left over. So notice I dropped out a step on this one. I didn't write the square root of 36 times the square root of 2. I didn't give them their own square roots. I just did that in my head. The square root of 36 is 6, and the square root of 2 is the square root of 2. So I dropped out one step. Number 7, 45 breaks down into 9 times 5. That's a perfect square. That's a prime. So this is square root of 9 times 5. Square root of 9 is 3, and square root of 5 is stuck because it's not a perfect square. Number 9, 343. 343, is that divisible by 2? I know it's not because it doesn't end in an even number. Is it divisible by 3? Nope. So on this one, we're going to have to keep going up a little bit more until we get to like 7. It's 7 times 49. So you could just keep plugging in numbers. You could do divided by 4, divided by 5, divided by 6, and divided by 7, and then, oh, yep, it gives me a whole number. So 343. Again, it's 7 times 49. 7 times 49. All right, so this one's a prime, this one's a perfect square. So we get the square root of 49 times 7. The square root of 49 is 7, and we have a square root of 7 left over because it's not a perfect square. Number 11, we've got a 10 out in front, so we just carry that down. And then 96, if we break that down, we already actually did that one up here, didn't we? Yep, that was the first problem. The square root of 96 we've already done. It's 4 root 6. So I don't need to do this again. I'm just gonna put a note here. Note from number 1. The square root of 96 is 4 root 6. So I can, instead of putting the square root of 96 here, I'm going to put, so this is multiplication, so this is multiplication. I'm going to put 4 root 6. Well, now I just multiply 10 times 4, I get 40 root 6. So that one was kind of nice, using something that we've already done on the worksheet. All right, number 13, 600 breaks down into 6 times 100. 100 is a perfect square, it's 10 times 10. 6 is 2 times 3, those are primes. So I have 7 from the constant out in front there, 7 times the square root of 100 times 2 times 3. The 7 again gets carried down, the square root of 100 is 10, and then I might as well multiply 2 and 3 back together because they're not perfect squares, so I can't take their square root, and I just get 6. So 70 root 6 is the answer to that one. On number 15, 180 breaks down into, I'm thinking 90 times 2. 90 times 2. 2 is a prime. 90 is 9 times 10. 9 is a perfect square. And 10 is 2 times 5. So on this one, I have a 2 squared times 9 times 5. So 5, carry that down from here. The square root of 180 is 2 squared times 9 times 5. So on this one, the square root of 2 squared, the square root and square will cancel out, just leaving me with a 2. The square root of 9 is 3, and then the square root of 5 is left over. Multiply all these numbers together. 5 times 2 is 10. 10 times 3 is 30. And I still have that root 5 left over. So 30 root 5 is the answer to number 15. All right, 3 more to go here. Number 19, 8 times the square root of 27. 27 is 9 times 3. 9 is a perfect square, 3 is prime. So this is 8 times the square root of 9 times 3. 8 times the square root of 9 is 3. And then I have a root 3 left over. 8 times 3 is 24, so 24 root 3 is the answer. 2 more to go. 900 breaks down into 100 times 9. Those are both perfect squares, so that's kind of nice. So this is 3 times the square root of 100 times 9. 3 times the square root of 100 is 10. The square root of 9 is 3. So I just need to multiply these together. So 3 times 3 is 9, times 10 is 900. So on this one, it was actually 900, the square root of 900 is actually 30. So I didn't think of that initially. 900 is a perfect square. So this is really just 3 times 30. So I should have checked to see if that was a perfect square right away. So I'm actually going to erase my work here. The better method for this problem would be to check if that is a perfect square right away. So just like on this problem number 22, you're going to want to see if that's a perfect square right away because that's a huge number. If not, you might have a really big factor tree. Same thing with number 20. You want to see if that's a perfect square first and then make the factor tree if you have to. So 900, the square root of 900 is 30. So this is 3 times 30, which still gives me that. I might have misspoke before and said 900. It should be 90. I apologize if I did. So this one is 90. 3 times 30 is 90. All right, on 23, 1,215. I'm trying to break that down. Let's see first, is that one a perfect square? 1,215. Is it a perfect square? Nope, because I did not get a whole number out. So I do need to break this one down. It ends in a 5 or a 0, so I know that it is divisible by 5. So 1,215, if I divide by 5, I get 243. 5 is a prime, so I'm going to circle that. 243, if I divide that one by 7. Nope, just kidding, it has to be 3. 243 divided by 3 is 81. So 3 times 81. 81 is perfect square, 3 is a prime. So carry down the 11. The square root of 1,215 is the square root of 81 times 5 times 3. So I carry down the 11. The square root of 81 is 9. And the square root of 5 times the square root of 3 is the square root of 15. I can't take their square roots because they're not perfect squares. 11 times 9 is 99. And I still have that root 15. So 99 root 15 is the answer to that one. All right, so again, I will keep the answers here for you. use them to your advantage, but please do not just copy the answers down. I will give you almost no credit. And again, you are supposed to copy down the work that I have just done and use that to help you complete the other problems. The steps are very similar, it's just the numbers that are different, but you still start this problem by making a factor tree. If you have any squares like this, you could write them as, in this case, 2 squared, and then ultimately you would cancel out the square and square roots, and you could go about the problem this way. If you have one like the square root of 18, it's actually going to turn out to be very similar to this if you use 9 times 2, and then you would take the square root of 9 and leave the square root of 2. So use these to your advantage, but please show me some work if you want some points for this assignment. All right, thank you.